Okay, so what I'm going to talk about next is Doppler. So this is Doppler. The Doppler, let me do it this way, Doppler frequency first. The best way to explain Doppler frequency, and it is a Doppler frequency, but it's for sound. If you've ever been to an automobile race or anywhere where there's very fast motors coming at you and going by you, as they get closer and closer, what you hear is, and once they pass you, now the RPMs of the engine haven't changed. So you might say the frequency that the sound's actually being transmitted at hasn't changed, but the wavelength changes because the speed of sound is the limiting factor. And as it goes away, the wavelengths elongate and it sounds lower. When it's coming to you, the actual wavelengths will shorten relative to the free space non-moving wavelength. And I should say really to the atmospheric wavelength. That's Doppler. It's the same way with electromagnetics. Now, you can do this using a relativistic approach, but you don't need to. If you do this in a very general way, you can say you have an antenna here, and it's a radar, and it's transmitting, and here's my target. I'm going to assume that this target is moving with a velocity VR towards the actual radar. This is real important that you understand. The only thing that matters with Doppler radar is the component of the velocity of the object in the direction of the radar. This is the radar. I want to figure out the Doppler frequency, which is going to be the change in the actual frequency from the from the non-motional frequency, from F naught, the transmitter frequency. All right, the whole deal is figure the total round trip path. So I go, this is the steps. You go 2R. That would be the total distance the signal moved as it was transmitted and returned. Do you agree with this, class? Now, this is non-relativistic, so I'm assuming that this thing's moving much less than the speed of light. Then if you divide that by the number of wavelengths, now you have the number of wavelengths that are associated with the round trip path. This is the total distance divided by wavelengths. It's the number of wavelengths that the actual signal, how far it moved in wavelengths. Now, if you multiply this by 2 pi, now you have the total amount of radians that the signal changed by from the time you transmitted to the time it came back. And this is an important part. You can see that this is really 4 pi, and then it's going to be over lambda times r. And that's the number of radians that the actual signal changed by. And here's where the Doppler shift comes in for the non-relativistic assumptions. If you take the derivative of the number of radians with respect to the distance r, you get 4 pi over lambda. Lambda is the free space wavelength. And then you get dr dt. Now, remember, I mentioned that the thing I care about for the Doppler frequency is the actual velocity component in the direction of the radar transmitting. And that is dr dt. So you can write this as simply 4 pi over lambda. And instead of dr dt, you can just put v of r. That is the phi dt. Well, that is really omega Doppler. Omega is a radian frequency it's really radians per second change. Omega is always related to the frequency itself by 2 pi f. So you can say that 2 pi f, and I might as well call this f Doppler at this point, is equal to 4 pi over lambda times v of r. And you can see that if I divide by 2 pi, I have f Doppler, and this is Doppler frequency, is equal to 2 over lambda, call it lambda naught, times VR, and that's as good as it gets. Something I might ask on a quiz or a test. If I have a radar here, all right, and I have a plane here, doesn't matter what distance it is, and the plane's flying at an angle with respect to the radial distance. So I want the component of that velocity in the direction of r. Now this is, I should say, this is just velocity v of this object. You might say v of the plane in magnitude, but the velocity in the direction of the radar would be, and this would be v of r, and that would simply be the magnitude of velocity times the cosine of the angle theta. And theta here is the angle that the velocity vector makes with the radius vector r that connects the radar to the target. When I look at the Doppler frequency for this one, and it's not a function of anything but the velocity of the target in the direction of the radar and the frequency that the transmission is occurring at. So if I just, for this one, the actual Doppler frequency would be 2 over magnitude of, or over lambda naught times VR, and that's magnitude of V times cosine of theta. What would the Doppler shift be if the angle was 90 degrees? 0. And here's something I'll tell you. We have a greyhound. We took her to Greystock, and it's a thing that they do in Georgia, and they had a deputy sheriff with a radar gun, and he was taking the velocity of these animals, and he found out my dog could run, I think it was 41 miles an hour, got clocked at. Some dogs got clocked at 46 miles an hour. But the thing I also noticed is that he had to be right in line with the dog the way he's running. The further off he got to the side, or the larger the angle between the dog's velocity and the actual location of the radar gun, the lower the velocity got. And with police radar, if you've ever noticed that, they usually try to get real close to the street and aim it right down the street, because as they get further and further away, they don't read the true velocity, and they don't have the ability to account for the angular, you might say, skew or the reduction, because they're not in direct line. So suppose I have two planes. I have a plane here, I'll call it 1, and it's flying at a 45-degree angle with a velocity V magnitude equals 100 meters per second. Now I have another plane. Now remember, I'm showing this with respect to the horizontal. Then I'm going to say I have another plane here, and it's flying at an angle of 30 degrees, and the magnitude of this velocity is, say, 200 meters per second. It really, this distance r here doesn't matter. You have two planes, you might want to say there's another plane here, and it's flying in this direction. This one's flying in this direction. Suppose this first one is transmitting a signal. So I want to know, what is the Doppler shift it sees? You find the component of velocity of the first, or the transmitter, in the direction r that links the two, then find the component of the velocity of the second plane in the direction of r. So if I look at this, I can say, well, this one has got a velocity that's closing, or it's reducing the distance between the two, so it's positive. I'll just say that what I'm looking at is VR1 here, and this one is the same. So the velocity here is VR2, and they're both causing the actual distance between the two planes to decrease. So when I look at F Doppler, I know it's always 2 over lambda. We'll get lambda in a second. Say the transmitter is equal to 300 megahertz, and some of you know why I did that, because then the wavelength is C over F is 1 meter, to make my life easy. And then it's equal to, well, the velocity, it's really the velocity, radial velocity of each of these added together on the component, or the component of their velocity in the direction of r. The thing you have to be careful about, if one is approaching, that would have a positive sense for that component. If the other one is approaching, it's a positive sense. So they're both positive. For this case, it's going to be V1, or it'd be 100, then it's times cosine of 45 degrees. For this one, I had 200, so it's plus 200 times cosine of 30 degrees. And if you put a wavelength of 1 meter down there, and you add these up, you get a Doppler shift. It's really 2 times, well, the cosine of 45 is 1 over square root of 2, so it's 100 over the square root of 2, plus, and then it's 200. And what is cosine of 30? It's square root of 3 over 2, I think. That would be the Doppler velocity. Now I have to tell you what actually is received back at the radar in terms of an actual frequency. And it would be positive. If it's positive, what you actually receive, we transmitted at 300 megahertz. I want to show you this and realize the problem. Here's the frequency. We transmit a signal of 300 megahertz. So I'm trying to show you the signal, transmission signal strength. This would be versus F, say if we had some sort of a spectrum analyzer. And this is going to be at 300 megahertz or F naught. The Doppler frequency is positive. Send out a signal of that. When it receives a signal, it's going to be much less in strength, but it'll be at F naught plus F Doppler. And you can see that this is extremely small. I don't know, what is this? So all this is the order less than 500 hertz. We're at 300 megahertz. This shift in frequency is tiny. If you have a frequency of 300 megahertz, let's go ahead and say that the received signal at 500 hertz, then this is received that's in hertz. That's the signal you receive. You see how close these two are?
The fundamental is 300 megahertz, or the initial, whatever. Are you saying that you receive less than what's transmitted?
More, right?
You receive more than what's transmitted.
It's a higher frequency. If the Doppler shift is positive, if you think about this, if our distance is getting smaller as the aircrafts are flying, it's going to be a positive Doppler frequency. If it's getting larger or they're moving away, it would be a negative, or it would lower the frequency. Now, the real thing I'm getting at, though, is the difference between 300 megahertz and 300 megahertz plus 500 hertz is almost insignificant. That's why with radar, you need what's called a very stable local oscillator, something that's going to be, if you're transmitting at 300 megahertz, it's 300 megahertz plus or minus like 0.0001% as far as the drift in frequency. There's ways to do this. Then when you receive the signal back at this frequency, you multiply it by a sine and a cosine at the same transmitter frequency, and you'll get sum and difference terms. Then you can use a low pass filter, but this is really quadrature filtering. You'll get rid of the high frequency component just by putting it through a low pass digital filter. If you transmit a signal, let's call this the radar, and I'm transmitting at F naught. So it goes out and it hits a target. Let's make it perfect, coming right at the radar. Then I get a return signal here at a frequency of F naught plus F Doppler. It's positive. F naught may be 300 megahertz, and F naught plus FD might be almost no different. Here, this frequency, if it's 300, and if I tried to just create a high frequency filter that would shunt this out and pass this, it's virtually impossible without an active component. You can't do it. The difference between these two is so small, you wouldn't be able to do it, even with a very high level, like, I don't know, 10th order Chebyshev filter or something like that. Just wouldn't be able to do it. So what they'll do is, now this signal and this signal are both going to have a cosine of omega t property. So they receive this signal. I'm going to just say they receive, signal received of t would be some magnitude. It's going to be, just say it's A received, and it's going to be the cosine of omega naught plus omega Doppler t. That's received. They take this and they beat it, and that's received here. And it's going to come, they'll split it up, and then they'll multiply this here, and this will be a cosine of omega naught t. Take it down here. This is a simple block diagram. And they'll multiply this by a sine of omega naught t. Now, both of these come off. And you know, if you have like cosine A times cosine B, cosine squaring here, and you're going to get sum and difference terms. And here you're going to get sum and difference terms. I don't want to go too far afield in this. And you put it through a low pass filter. Oh boy, how far do I want to go in this one? Okay, let me see here. I think I'm going to leave it like this and deal with this in class. But when you do this low pass filter on this one, you're going to get just the low frequency component of this. You'll just get this cosine. Basically, it'll be the value of A times cosine of omega Doppler. And here it's going to be A times sine of omega Doppler. I'm not accounting for a little phase change in both of these, but really what you can do is extract the Doppler frequency. And I know I'm not being very clear about this, but I will do that in class. And this is basically, did you have quadrature filtering in phase and quadrature class? Filtering is really trying to extract a portion of a signals of a frequency range or a signal over a given limited frequency range. And the only way to do that, like if you have, I mean, what is, or a cosine squared of omega naught plus, I just call it omega naught t. Well, that's really what, a times 1/2, and it's plus 1/2 cosine omega naught t. Do you remember that? It's a half angle formula. This is DC. This is very low. This is very high frequency. When you put a low pass frequency, you get this. But more than that, you'll also, I just put omega naught there, you'll get the cosine of omega d there, and you'll be able to get the Doppler shift. I'll have to do this in class. But when you get into things that are moving close to the speed of light, there are some adjustments you have to make. But anything in terrestrial down here on Earth, you don't have to worry about. I'm only mentioning that because some of you may work with NASA or Elon Musk with his Starlink or something like that, and they may be doing work where they're going to have things that are moving at velocities, or at least they have to consider meteors and things like that moving at velocities approaching the speed of light. And again, this is not my area of expertise, but the only time you really have to worry about the relativistic Doppler shift is when something is moving close to the speed of light. And outside of a black hole exploding, can't think of anything, any natural thing moving that fast. I mean, a mass item. So we did the full, how to figure out from an antenna's transmission to reception. 846 is this one. It says, consider a pair of half-wave dipoles at 2.45 gigahertz separated by 50 meters in a line for maximum power transfer. If the output power must be at least 35 dBm to be detectable, calculate how much power is required to drive the transmitting antenna. Assume that both antennas are 100% efficient. Got two antennas. Here they say this is 8.46. Two antennas, and they give you an operating frequency of 2.45 gigahertz, and they have a separation distance of 50 meters, and they're aligned for maximum power, and they're half-wave dipoles. And so this is 90 degrees. Basically, you got two half-wave dipoles looking right at each other. And this would be 90 degrees. This would be 90 degrees. And they say if I have a certain amount of power that's transmitted, how much power is received, or vice versa. And he gives you a specification. They want the output power. Now, I'm going to tell you about this one. He doesn't give you a load, so he really is talking about the power received. He gives you really power received here is equal to minus 35 dBm. Here's what it looks like. Two antennas, both half-wave dipoles. The first thing I want to do is take this and turn it into, this is not in terms of watts, it's dBm, right? So how do I take this and turn it into watts? So power, if you want the units in dBm, are what? They're 10 times the log of the actual power, and this power is in watts, it's linear, right? Divided by 10 to the minus third. This is a relationship at power in dBm, which is here. This is in dBm, or dB really. dBm is the unit. Now look, if I got power in dBm, and I'm going to do it. So I have this power right here is minus 35 dBm. That's equal to 10 times the log. That is a log base 10, by the way, of the power. Now this will be the linear in watts over 10 to the minus third. So if I divide 35 by 10, I get minus 3.5 is equal to the log of P over 10 to the minus third. Now I have to, whenever you have a log on one side and you're solving for something inside of it, you take everything to the power 10 or E, depending on if it's a natural log. So this becomes 10 to the minus 3.5 is therefore equal to, and if I take 10 to the power log of that, it's just going to be equal to P over 10 to the minus 3. So that means that the actual power in watts would be what? 10 to the minus 6.5 watts. And what is 10 to the minus 6.5? And that's not much. That's the power received. And remember, P received, right, over P transmitted is equal to what? Lambda over 4 pi R, right, times gain of transmitter, or it's squared, right? Gain of transmitter, gain of receiver. Do you remember that? That's really called the Friis equation. I got P received, I want P transmitter. These are half-wave dipoles, aren't they? And he says you can see that now it's just a matter of solving for P trans. So P trans, the transmitted power, is going to be equal to the received power. It's divided by all this. So it's going to be divided by lambda over 4 pi R squared, gain of transmitter, gain of receiver. We have P received. What is the wavelength going to be, guys? C over F, right? And F is 2.45 gigahertz. I'm not going to put a value down yet. R is 50, I believe. Now, what is the gain of the transmitter? Which is the gain of the receiver, right? Because they're both half-wave dipoles. The maximum gain.
1.64.
Now, this is the kind of problem you should know how to do without much hesitation. So that means now I'm going to just put this in MathCAD and solve it. I'm going to solve this equation to find out what the transmitted power is. And I get 3.096 watts. He has 3.2 watts. So I'm sure it's rounded. So for 8.51, refer to figure 8.53. It's two dipoles separated by 100 meters, source resistance of 50 ohms, and the other has a load of 50 ohms. Now, this is a great problem, but think about those antennas not being in them for maximum gain, but one tilted. That's the kind of problem I'd be ready for in the exam. First antenna, you have 50 ohms here. You have a source voltage. I'm exaggerating this, of course. R, and this is 50. Then you have a distance away. You have a second antenna. I don't know, are they both the same? It has a voltage here, Vs is equal to 12 volts. That's 50 ohms. All right, so these are exact half-wave dipoles. And then this has a load of 50 ohms, right? And the frequency of transmission is equal to 500 megahertz. This distance R equals 100 meters. So what they want, what Whitworth wants is this voltage, the voltage across the load. So with all this considered, where do you start and how do you get the answer? This is like a classic problem you might see in the exam. Matter of fact, almost guaranteed you're going to see something like this. Only I'll probably tilt this antenna. This might be a half-wave dipole. This might be a short dipole. In other words, I can take this and change the actual settings a bit, but same concept. So where do we start, Kenan?
The current.
Exactly. I'm going to draw the actual equivalent circuit to the source. And what I want is this antenna current, the actual antenna current right there. So this is 12 volts. Here I have a resistance of 50 ohms, right? Now I'm going to put in what the antenna is, 73.2 plus J42.5. And I need this current, right? All right, how do I get that current? So it'd be 12 plus, it looks like 123, right? 0.2 plus J42.5. What's the third step? Now I got that, what am I going to do?
Transmitted power, 1.5 squared per rad.
Now what, Keith?
Average power density.
Let's get PAV right here. I want the average power density incident there. How do you get that?
P rad over 4 pi r squared times gain of transmitter.
Transmitted power, right? Over 4 pi r squared, but there's something we got to do. The exact half-wave dipoles. What is it? So this would be the isotropic power density, right? What do I multiply this by to get the actual power density? The gain, and it's maximum gain, so it's 1.64. All right, now I'm going to put that down here. That's watts per meter squared. What's the next step?
T received.
What is that?
That times the aperture.
Just
Average power density times the aperture.
It's average power density time. And what's the aperture?
Lambda squared over 4 pi gain of the receiver.
Lambda, it's just times the gain, right? Aperture would be lambda squared over 4 pi times the gain, which is, yeah, and that would be the power received in watts, right? What next? We need V open circuit. Now what I'm going to do is draw an equivalent circuit of this receiving antenna with VOC, and I hope y'all can see this. So here I have plus to minus VOC that we'll calculate. Then I have to put, and this is the internals of the antenna. We're putting an equivalent circuit. Now you're going to have the radiation resistance of the antenna, RRAD, which happens to be 73.2, and the reactive component, which is, I'll just put JX antenna here. We know it's going to be the same as the transmitter. And then now these two dots that I put here indicate that now I'm external, and that's connected to 50 ohms. And what Wentworth wants is this voltage right here. He wants the load voltage. How many remember what the open circuit voltage is in terms of the received power and the radiation resistance? You remember it's the square root of 4 times P received, right? Times R rad. So now once I have the open circuit and I have all this, what do I need to get this voltage? Just think about it. That's the voltage, open circuit voltage, right? If I take that and multiply it by 50, and then divide it by 50 over the sum of these two, then it's voltage division. That's how you get it. I'm going to put it on MathCAD. I like MathCAD. If the tilt angle of the receiving antenna is not at 90 degrees, where you're talking about, there's a tilt angle you're talking about if this angle here, suppose the antenna changed like this, suppose the antenna tilts, all right, where now instead of being 90 degrees, it's something less than 90, and this is the receiving antenna. What actually happens is now the gain or directivity of this antenna goes down. So now the directivity or gain, and I'm going to put gain on the receiving antenna, now it's going to be a maximum of 1.64. Now that's an exact half-wave dipole. So you have to say it's times the cosine of pi over 2, cosine of that angle, whatever it is, over the sine of that angle, and you have to square it. Now that's going to be how the gain is reduced. Now that's if it's tilting in the plane of the paper like this. If it's tilting and it's tilting this way coming out, now that would be the cosine squared of the tilt angle. Usually when they say tilt angle, they mean the angular difference of, if you think about the two axes of the antenna like this, it's how on an axis that you might say if you take a radius vector and just draw it through the centers of these two, and then twirl this thing on the perpendicular axis and find the angular difference between the two, that is considered the tilt angle. But if it was skewed the way I showed you, then the gain would change. And I think that's very important because on the exam, I'm going to ask something not about tilt angle necessarily, but definitely about how if the antenna is got an angle that's not 90 degrees, how does it affect things? And I'll give you the directive, like the angular function that would go in that for the with the right directivity, because I know most of you, not for a short dipole, but for a half wave, I'll give it to you.